In this video, we are going to examine the absolute or global extrema of a function. So this is our last topic that we cover in function analysis. Let me review with you. A relative maximum is the maximum y value only in a certain interval or a certain neighborhood. A relative maximum would be just a hump, any hump in a certain interval. Similar description of a relative minimum. The absolute maximum is the maximum y value of the entire function, sometimes on a closed interval or on the entire function. But it is there's only one maximum y value. Similar for an absolute minimum. Okay? We have the extreme value theorem. The extreme value theorem says if a function is continuous on a closed interval, then that function has to have both an absolute maximum value and an absolute minimum value. And it totally makes sense. If we have a curve with it's on a closed interval, it has to have an absolute maximum value and an absolute minimum value. That absolute maximum value could be at a relative max, or it could be at an endpoint. If this endpoint went up a little bit higher and stopped up here, that would be the absolute maximum value of this curve. So that's the extreme value theorem. If a function is continuous, it has to have an absolute max and an absolute min on a closed interval. All right. So the absolute maximum of f is the largest or highest y value of the curve. The absolute minimum value of f is the smallest, lowest y value of the curve. Okay, it does make sense that every continuous curve on a closed interval must have an absolute extreme, both an absolute max and an absolute min. Okay, could the absolute max or the absolute min occur at more than one x value? Well, of course. If the maximum y occurs at two different spots, it could have two different x values, but there's only one absolute maximum value of the function. Could the absolute max or min occur at a value of x that is neither a relative max nor a relative min? Yes, if it's at an endpoint. So yes, since the absolute max min could occur at an endpoint of the interval. Okay? Alrighty. When you are asked to find an absolute max or an absolute min, we only examine the possible x values at which the absolute max or min can occur. A convenient method that you can always use for this is known as the candidates test, and the candidates are the x values. So it's also known as the closed interval test. Either phrase is fine. Okay, so let's take a look at how we can apply that. What is the minimum value of g on this interval? When it says the minimum value, they are talking about absolute or global. They are not talking about a relative min. If they meant relative min, they would have to say relative or local min value. Okay? So we're looking for the absolute minimum value. So let's see. Whenever I see that, whenever I know I'm looking for an absolute min value, I need to apply the candidates test. And it's just a nice little chart that helps you organize your thoughts. We're going to list the x values where the absolute min can occur And we are finding the minimum value of G, so I need to finish my chart here. If I'm going to use it, I'm going to finish the chart. We're finding the minimum value of G, so we put G up there. If we were finding the minimum value of F, we would put F there. If we were finding the minimum value of G prime, we would put G prime there. Okay? All right. Our candidates for X. Our candidates for X are either a boundary or the location of a relative min of G. Okay? So I'm going to begin with my boundaries. And for the sake of your notes, I'm going to say here, those are our boundaries. Okay? I'm also going to include here the location of any relative minimum value. What makes a relative min value? What do we do to check for a relative min value? We look for critical values. So right here are going to go the critical numbers, the critical values of X. So to find those critical values, we take G prime, set it equal to 0. Or find what G prime is, what value of X makes G prime undefined. So G prime of X is 4x cubed minus 32. I'm going to set that equal to 0 to find my critical numbers. Nothing makes G prime undefined, so we won't have any numbers from that. I'm going to factor out a 4. I'll have x cubed is equal to 8, so x cubed, is equal to 8, so x must be 2 here. So 2 is our only critical number. Sometimes you have several, but 2 here is our only critical number. So these are the x values, these are the only x values that could make the minimum value of G. So how are you going to find out which of these work? Well, you're just going to find the G value at each of these and pick the lowest one. So I'm going to go back to my G function and find G of 3, G of negative 3, and G of 2. So for G of negative 3, I'm going to have negative 3 to the 4th is a positive 81 minus 32 times 3 is 96 plus 4, let's see, that is negative 96 plus 85, so that is negative 11, I think. I'm going to do the same thing for G of 3. 3 to the 4th is 81. Oh, did I? When I put negative 3 here, when I put negative 3 here, that should have been a plus, right? Okay, so it's not negative 11. And it's 181. Okay, when I put positive 3 here, that's going to be my negative 96. That's going to be my negative 11. And now I'm going to put 2 in for X. 2 to the 4th is 16, minus 2 times 32 is 64, plus 4, and that's negative 64 plus 20, so negative 44. So on this interval, the minimum value of G is this negative 44. It occurs when X is 2. What did they ask us in the problem? What is the minimum value of G? So the minimum value of G is negative 44. So that's what I'm going to say. The minimum value of G,
here's what I found,
is, is negative 44. Okay. All right. Did not realize my speaker was on over there. Okay. Sorry about that. Okay. Next example, number 2. What is the absolute maximum value of H is equal to this on this interval? the absolute maximum value. So immediately I think candidates test. Or you can think of it as closed interval test, either way. Okay, so I'm going to, my variable is x, so I'll put x here. We are finding the maximum value of h, so I put h here. Okay, by the way, I didn't say this on this problem. I got distracted. But I didn't say this. It says to justify your answer here. Our justification is this completed chart, okay, with the work shown to get these values. Okay, that is our justification. Okay, this is a widely recognized justification for an absolute min or max. You must show the work that was used to get these values. Okay. All right. So we're going to fill out our chart. Now, if you're going to use this as your justification, this chart has to be complete, including whatever the function is right here. Oftentimes, students will leave this blank. That is crucial if you're going to use this as your justification. If you plan to justify it a different way, then no, you don't have to complete this chart. Okay? So, I'm going to begin with the values on our closed interval, and I'm going to say where I got those from. So these are my boundaries. And then I'm going to include any critical numbers, particularly the relative minimum x values, the x values that make the relative maximum. Okay? Because the absolute max can occur at a boundary or a relative max. So we really only are concerned with the relative maximum values, the x values that make the relative maximum. Okay, anyway. All right, so to get these critical numbers, I'm going to take my function, take its derivative. The derivative of ln of x squared is u prime over u, so 2x over x squared. That is 2 over x. Okay. When we set this equal to 0, no value of x makes this 0, but x equals 0 makes this function undefined, right? So I'll say that no x value makes h prime 0, x equals 0 makes h prime undefined. Okay? However, x equals 0 is not in our interval that we're looking at. So I'm going to say that. However, where should I put that? Right here? However, x equals 0 is not in 1 to 3. So I have no critical numbers that belong on this chart. Okay? If we were doing something else on this, we might need to include 0. By the way, x equals 0 makes h prime undefined. Is x equals 0 even in the domain of this function? No, because the argument of a natural log has to be positive. Okay, so x equals 0 is not even, it's on the vertical asymptote there. Okay. All right, let's go back here. So the only candidates for our absolute maximum value are x equals 1 and x equals 3. To find out which one is the maximum, I'm going to just find h of 1 and h of 3 and see which one is highest. So h of 1 will have ln of 1, which is 0. h of 3 will have ln of 9, which is greater than 0. So I have 0 and ln of 9. So the maximum value of h, which is what they were asking me to find, is ln of 9. My justification is my work that I wrote. Okay? All right, let's take a look at this function. Let me zoom out a little bit. Okay, so I can get it all on there. We are given the graph of f of x, y equals f of x, shown on the right from x equals -3 to x equals 3. And we are told that f has horizontal tangents at x equals -1, so this has a horizontal tangent here, and x equals 2, and zeros at x equals -2, so this must be -2 here, and x equals 2.8, so this must be 2.8 right there. Okay, let's answer these questions. State the absolute maximum value of f and the absolute minimum value of f on the closed interval -3 to 3. Well, on the closed interval -3 to 3, the absolute maximum value is 9, and the absolute minimum value here is -2.7. So max is 9, min -2.7. Okay? Now they ask us state the absolute max and the absolute min on the open interval -3 to 3. So now we're not including exactly at -3 and exactly at 3. So what is the absolute max and the absolute min now on this open interval? Well, a lot of students here will say the absolute max is 9, but on the open interval, does the y value ever reach 9? It does not. It gets very, very, very close to 9, but we cannot state a value that's close enough to 9 that doesn't reach 9. So there is no absolute max on that open interval. Same thing for the absolute min. There is none. So no absolute min on that open interval. Let's state the absolute maximum value of f and the absolute minimum value of f on this interval. -2, closed on the -2, open on the +3. So we're open here but closed here. So I'm ignoring this part of the graph here. What is the absolute maximum value now? Well, the absolute maximum value clearly occurs when x is 2 and y is 1.8. So the maximum value here is 1.8. What is the absolute minimum value? The minimum value would be the 2.7 if we ever reached it, but we don't. So there is none. No absolute minimum value. Okay, what about open interval on the -3, closed interval on 2.8? So this time we're ignoring this part. It's open interval on this one. So the absolute max would have been 9, but it never reaches it. So no absolute max. Oops, no absolute max. Okay, the absolute minimum value would be this -1.6. Okay, so that's how it works if it's not a closed interval. One more example here. Let us find the absolute extrema, that means both, of this function on this open interval 0 to 3. So it's easy to examine these when you're looking at the graph. It's not as easy to examine them if you're given the function. So let's take a look at this. First of all, absolute min or max, or in this case both. This means we're finding both. Okay, closed interval test or candidates test. So I'm going to set up the closed interval test, the candidates test. X is my variable. What are we finding the extrema of? Of f, so f goes right here. Okay, what are my candidates? Well, usually we start with our boundaries, yeah? And I am going to start with my boundaries, but I do recognize that these boundaries are not ever going to be reached. So to denote that, I'm going to write I am going to 0. That little arrow there I use to denote going to. I'll write that for your notes. Going to. And same with the 3, it'll never reach 3. So we are just going to 3. That means whatever f value is here, we will only be going to it. Never will reach it. So if one of these is our absolute max or min, then we will say that there is none there. And look at some of the choices. There are some choices that say f has no max and no min. Okay? Down here. Alright? So we'll have to keep that in mind. So those are our boundaries, but I'm also going to put on any critical numbers. Okay, let's go. Alright, so here's our function. And I'm looking at our function, and I notice that there are an awful lot of x's here, right? There are an awful lot of x's, no constant value here. Is it possible, you guys, to do our quickie divide? 2x to the 4th divided by x squared. Negative 8x cubed divided by x squared. 5x squared divided by x squared. Is that legal to do here? Normally, you couldn't just do that, but because there is a value of x that makes the denominator 0, but 0 is not in our interval. So we can totally do that. Only because the 0 is not in our interval. Okay? Otherwise, we couldn't do it for every x value. We would have to examine that. Because when we take out this denominator, we're losing part of this function, right? We're losing a whole in this function because you can factor out an x squared, and that makes a whole. So when x is 0, we have a whole in this function. But since we're not including that 0, we can just go ahead and divide it out. So I'm going to go ahead and divide it out. We'll have 2x squared minus 8x plus 5. Now all of a sudden this looks really nice. Okay? Well, a lot nicer than that. So f prime is equal to 4x minus 8. I'm going to set that equal to 0. The value of x that makes that 0 is 2, which is in our boundaries. So I'm going to put that on my candidates test. Okay, the only thing left to do is find f at each of these values. So f at 0, f at 3, f at 2. Now, keep in mind that we're not ever going to reach that 0 and reach that 3. So truly, instead of being f at 3 and f at 0, this would be a limit as x approaches 0 and a limit as x approaches 3. F of 2, we just find f of 2. So the limit as x approaches 0 of f, here's f, the limit as x approaches 0 is 5. The limit, I'll put 5 here, we're going to 5. The limit as x approaches 3 would be 2 times 9, that's 18, minus 3 times 8, that's 24, plus 5, so that is 18 plus 5, 23 minus 24, so I got a negative 1. So we have those. For f of 2, we just find f of 2. I'm going to do it over here because I don't have room right there. F of 2, 2 times 4 is 8, minus 2 times 8 is 16, plus 5. Okay, 8 plus 5 is 13, minus 16 is negative 3, so negative 3. Okay, so which one is the highest? 5 is the highest, but we never reach it. So I will say here, no absolute max. Which is the lowest? Negative 3, and it does reach it. So the absolute min is negative 3. Okay, so which one is that? No max, min of negative 3, B. Okay, so that is absolute or global extrema.